Okay, these were the questions for homework 3. The first one was show that x and y operators correspond to the projection on the xy axis and also pi degrees, 180 degrees or pi radians of rotation around x and y axis on the Bloch sphere. So we had shown this for the Pauli Z operator in the class. Now similarly for the x and y operators. X operators, as you remember, is 0 and 1, 0. This was the bit flip operator. And y was 0 minus I and I 0 operator. So if you apply, let's take the case of cat 0, right? If you apply the x operator on cat 0, that means x operator was 0, 1, 1, 0, and you apply this on 1, 0, which is cat 0, you get 0, 1, which is cat 1, right? So x operator flips the state to 1. Similarly, if you apply x on cat 1, you would obtain cat 0. So this is 180 degrees or pi radians rotation around the x-axis on the Bloch sphere. Like 0 is transformed to 1 and 1 is transformed to 0. So if it is true for the basis, then it would be true for all qubits, right? Any generic qubit that one could represent alpha cat 0 plus beta cat 1. So if this is true because of linearity, right? If you apply the x operator to this, you would get alpha x0 plus beta x1, right? So individually on the basis, you would apply the x operator, and each one of them would flip by pi degrees, rotate by pi degrees around the x-axis. So this what x does on a qubit is to rotate by pi radians around the x-axis. So similarly, if you take, for instance, and this is, right, I have also got this over here. Like if you start with 0, right, cat 0, it is rotated to cat 1. So this is your x-axis. So this is the same as rotating by pi degrees around this x-axis. So similarly, if you operate cat 0 with y, right? This is 0 minus I 0, and this is cat 0. You end up with the column vector 0i. This is the same as I 0, 1. But this is like I cat 1, right? And we said global phases do not matter because they are not measurable. And this is equivalent to cat 1. So similarly, in this case also, the cat 0 vector is rotated around y-axis now to obtain cat 1. And if you similarly apply y on cat 1, right, you would also get 0. So 1 is rotated to 0, 0 is rotated to 1. So through the same argument, we can say any qubit, since it is rotating by pi degrees the basis, any qubit is also rotated because of the linearity of these operators. So you can also further check the effect of x on plus, right? So the effect of x on plus is this was x 0 1 1 0, and this was the plus state 1 over square root of 2 1 over square root of 2. Again plus, right? This is the effect of this. So this projects on the eigenstate plus. This would be normal because this is like the eigenvalue equation, right? This is operator operating on the eigenstate equals eigenvalue, which is 1 in this case, and this is the eigenstate. So this is the x-axis, and these are the eigenstates of the x operator which is the ket plus and the ket minus state. And you can similarly, you can use the same argument. You apply this is the y-axis, right? And plus I and minus I were the eigenstate states of the y operator. So operating with y on ket I, since I is an eigenstate, again this is an eigenvalue equation, you would obtain ket I. So y projects on the eigenstate I. The second question was, now we show that Bob can obtain 3 sets of classical bits, right? Using this circuit. This was part of our discussions, I think, on the superdense coding and teleportation. We want to show that using this circuit, right, which is remember the time is flowing from left to right. So this is your input. It's first operated with C0 and then operated with H, and then you have the output. But in the operator notation, it is in reverse order, right? Because you apply this operator on the input. So it's operated first with C0 and then H tensor product I. And this notation, right, what this means, it means that you apply the H operator, like as in this case, on the first qubit, and then the identity operator on the second qubit, because second qubit we don't apply anything. So this is denoted by H tensor I. And C0 is, of course, it's a 2-qubit operator, so it's operating on both of the qubits. So let's see. In the class, we had seen one of the cases, of bad states, but now we go over the 3 other cases. If the input is ket psi minus, right, to this. Now first, and this is the ket psi minus state, right? 1 over square root of 2 ket 0 1 minus ket 1 0. I first operate with C0, right? Operating C0, this doesn't change because this is our target bit. This is our control bit. The first bit is control, the second is the target. Control bit is 0, target bit is 1, so it remains the same. But on this term, control bit is 1, target bit is 0, so it flips the target bit and this becomes 1 1. So after the C0, this is the state I have. And then I apply Hadamard on the first qubit, right? Do nothing on the second, but apply Hadamard on the first qubit. If I do that, Hadamard converts 0 to plus and 1 to minus, right? And the state I have is 1 over square root of 2, ket plus 1 minus ket minus 1. If I plug in the plus and minus states in standard basis, right? This I end up with there is 1 over square root of 2, but because of the definition of plus and minus states, there is another 1 over square root of 2. I have ket 0 1 plus ket 1 1 minus ket 0 1 plus ket 1 1. These 0 1s cancel. These ket 1 1, these 2 states cancel, and these ket 0 1, they add up. So I have this ket 0 ket 1 states. In other words, I measure 0 and 1 in the standard basis. So if I have in the input bad state psi ket psi minus state, in the output I have 0 1. Similarly, all the other bad states are converted to the standard basis, with this circuit. So if I have ket phi plus state, which is 1 over square root of 2 ket 0 0 plus ket 1 1, I operate with C0, and then I operate with Hadamard on 1. I end up with the 0 0 classical states, classical numbers. And then if the input is cat phi minus, which is 1 over square root of 2, cat 0, 0 minus cat 1, 1. Again, I apply C naught first, and then Hadamard on the first one, I end up with 1, 0. Right? Since, as we discussed last time, these are unitary operators, they also operate symmetrically. And in the class, we had seen, in the input, if we have this standard basis 0, 0, 0, 1, 1, 0, 1, 1, they were converted in the output as to the Bell states, corresponding Bell states. But the reverse is also correct because these are unitary operators. If in the input, this time in the reverse order, in the input, we have the Bell states, in the output, we have the standard basis, the classical bits 0, 0, 0, 1, 1, 0, and 1, 1. Okay, the last question was in the teleportation protocol, what should B do on his qubit if A sends 1, 0, and 1, 1 to complete teleportation? And such that the B's qubit becomes alpha cat 0 plus beta cat 1. Remember, this was the initial qubit state that Alice had, and Alice wanted to teleport this to Bob, to this state. And we had seen in the class, what would happen if for the cases 0, 0, and 0, 1, right? What kind of operation we would do to recover, to teleport this state. But now, let's suppose, remember there were 4 states, and Alice was doing a measurement on her qubit, and the outcomes were equally probable, 1 over 4, with probability of 1 over 4 each one of them. So in case Alice measures cat 1 and cat 0, now, according to the protocol, we had seen B's qubit, Bob's qubit collapse to alpha cat 0 minus beta cat 1. Right? I have this one. So how should I operate? What is the single qubit operator that I need to use to convert this qubit to the qubit that we want to recover? The answer is I operate with the sigma z operator, poly z operator. If I do that, this poly z keeps cat 0 the same, but converts cat 1 to minus cat 1. So this minus beta cat 1 becomes plus beta cat 1. So I recover, the qubit that Alice wanted to teleport. So this is the first case. The second case is when Alice measures cat 1, 1. Then in this case, according to the protocol, B's qubit collapses to cat alpha cat 1 minus beta cat 0. What should I do to convert this to this state that Alice wants to teleport? So in this case, I first apply the X operator, which flips the bits, right? Now, if I apply this because of linearity, this is alpha x cat 1 minus beta x cat 0. So x flips 1 to 0 and 0 to 1 with flip operator. So this becomes alpha cat 0 minus beta cat 1. And then now we apply z, right? This becomes alpha z cat 0 minus beta z cat 1. And z does nothing to cat 0, but it change the sign, of cat 1. So this becomes alpha cat 0 plus beta cat 1. So these are, this is what Bob should do in the other 2 cases of the teleportation protocol.